Hello everyone, welcome back to this 9th tutorial in the series Statistical Analysis in Python. And the last couple of tutorials we have been focused on correlation analysis, and in the first video, I hope you watched those. The first video of this mini series on correlation analysis, we looked at the standard correlation, Pearson, Spearman's correlation, and in the last tutorial we looked at how a third variable, a confounding variable, can influence the correlation of two variables and how we can account for that. And if you haven't watched those two, I highly recommend you going back and watching those two videos and coming back and picking it up at this point. Now, while you're doing that, this would be a great time to hit the pause, stop button and hit the subscribe button. And while you're there, look for the little thanks button if you're feeling extra generous. Okay, now what are we going to learn in this specific tutorial? We're going to look at a couple of advanced correlation analysis topics. And what do I mean by advanced? Of course, we have covered the top ones, and now we are looking at confidence intervals and statistical significance testing, just to delve a little deeper into what we're going to cover. The first thing that we'll look at is confidence intervals, because until now, what did we do? We just reported that the Pearson, R value, for example, is 0.653, for example, right? So now with confidence intervals, we can basically say that the R value is 0.653 with low limit 0.587 and upper limit 0.711 with a confidence of 95% and the p-value and total number of data points, right? So this is more statistical way. We are basically adding the statistical rigor to our Pearson's R value, for example. Okay, and we're going to use Fisher's Z. Again, I'll explain those once we get to the code part. And the next thing we're going to look at is comprehensive correlation matrix. Well, in this case, we're going to compute all pairwise correlations. We have multiple, right? For example, 6 pairwise correlations of these different factors. And then we report the p-values and confidence intervals. If you look at the output on the screen, there is something called, for example, Bonferroni correction that we're going to apply, or Holm, or one of these other FDR corrections. What does that even mean? Well, it's very simple. On the screen, you see it says 6 significant out of 6. What does that mean? Well, we tested 6 unique variable pairs. It's like flipper length versus build depth or something. You know, let's say we have these 6 unique pairs. Okay, we have 3 variables and then 6 unique pairs of these where we are looking for correlations. And of all those 6, upon applying these corrections, we realized that they still are correlated. So 6 out of 6 are significantly correlated after accounting for this correction. And what that correction means and other notes, we'll save that for our Colab notebook, because I plan on actually going through the background in the Colab notebook and then actually jump into relevant piece of the code. We'll also look at hierarchical clustering of correlations. What does that mean? If you just look at this plot like dendrogram. I always miss the second R. I call it dendrogram for some reason. It's dendrogram. What this shows you is, for example, these two inner ones are more correlated than the inner ones versus this, and the outer one is the one that's least correlated. We're going to look at that. And of course, this is a plot that's kind of reordered correlation matrix, which is basically the same correlation matrix we saw in the last tutorial, for example, except we kind of reordered to put these, let's say, correlated ones based on this clustering close by. So bottom right, you see more red. And as you go out, you see less red, meaning less correlated. That makes visualization easy. And we'll also look at Bootstrap confidence intervals for correlations. I hope you know what Bootstrap is. It's basically random sampling for your data and creating a new sample and doing whatever the test you want to do, and combine the results to infer something about your data. So we are going to apply Bootstrap resampling to estimate the uncertainty of correlation coefficients basically, I know you can read the screen, whatever the text is. So let me quickly summarize this plot. In this plot, it's showing you the correlation coefficients that we calculated from bootstrapping, random sampling, and then the spread of those correlation coefficients is kind of normal distributed right there, with the mean right there, bootstrap mean. In fact, the original R value and the bootstrap mean value are identical, so they fall one over the other here. And then how much is that actually spread? This is kind of important, and with 95% confidence interval, we can say that it goes between minus 0.84 or something to 0.89, whatever that value is. And even if you look at these extreme low and high limits, it's still statistically significant. What that tells us is the flipper length versus body mass are highly correlated, even with this low and high limits. That's what we are getting out of this bootstrap confidence intervals for correlations. And the power analysis is, I talked about this 3-4 videos ago. This is basically the same power analysis, right? How much data do you need to get attain certain level of power? For example, if you look at R equals to 0.3, which is the green line, then to get 80% power, you need at least 75, 80, 90 data points right there. In our case, we have 300 data points, so we should get significant power. With that quick background, let's go ahead and jump to our code in Colab. And again, as usual, look for the link down below under the description for the code. Okay, so I just reconnected and it's executing right now as we speak, and we stopped. I mean, there's a lot of text here because I realized I'll be sharing the Colab notebooks with you and not my PowerPoint slides. So why not add all my notes to Colab notebook so it stays with you? So that's why it's very wordy. And if you look up here, this is exactly where we stopped the last time in the last tutorial. Okay, and we looked at the partial correlation, and here is the analysis summary of what we learned in the last tutorial. But now we are going to jump into part 3, which is advanced correlation analysis. Okay, so what's new and advanced in this advanced correlation analysis? What we did not do earlier. First of all, we are adding statistical rigor to our correlation analysis. What do we mean by that? Well, earlier we got correlation coefficient of, for example, 0.65, and now we are going to add confidence intervals to that, right? So I already mentioned that during the PowerPoint slide presentation. And we are also adding multiple testing problem, which is we tested correlations one by one earlier. And now when you're testing 6 correlations simultaneously, we need to, the correct p-values to avoid false discoveries. Well, what does that even mean? In fact, let me skip through this because once I did this, I added a bit more deeper explanation when I'm talking about these specific functions. So the comprehensive analysis, the sentence I just ended earlier, basically what that means is earlier we have 6 correlations separately, right? We have these 3 variables and we are checking 6 correlations separately, and each with 5% chance of being wrong, because we are looking at 0.05, for example, right? 5% of being wrong. Now with 6 tests, we have 26% of being wrong because you're combining these 5% errors. Now again, how did we get this 26%? If you're down here, I added a note. So 26%, so given the alpha is 0.05 and n equals to 6 in our case, then to find at least one false positive, the chances are 1 minus alpha to the power of n. So basically when you plug the numbers in, you get about 26%. So that's exactly where that 26% chance comes into picture. So that's what I mean by multiple testing problem up here. So we'll look at that, and we'll also look at method validation, which is basically we assume that our correlation estimate kind of was accurate, but Bootstrap resampling is where we show how stable is this correlation if we repeated this study with n number of samples. We'll also look at advanced exploration. So looked at which variables behave similarly. This is where I showed you the dendrogram, and we'll get to that. And also study design. And finally, I'll show you how typically people report these, when you're reporting them in your publications. Okay, so I think that's with that. I think one other thing before jumping in that's worth mentioning is we have 4 different correction methods that we're going to look for to correct for our correlation. And Bonferroni is the most strict, and it rarely makes mistakes, but it might miss some relationships. Usually this is what most of the time people end up using, but since it's just changing the method in our line of code, let's go ahead and do all 4 and verify these corrections using all of these 4, and then see after applying corrections, do we still have statistically, excuse me, let me close this phone, sorry about that. Okay, so even after applying these corrections, do we have statistical significance when it comes to correlations? That's the question we will be answering here. And basically here, the way we report, the result is before any of this, bill length and body mass are correlated with an R value of 0.59. With this new extra stuff, we can say with an R value of 0.59, with a lower limit of 0.51 and upper limit of 0.66. And this remains significant even after correcting for multiple testing. This is how we can actually report. Yeah. Okay, and and a lot of visualization, again, which one exactly makes sense completely depends upon, first of all, your taste and your audience. But there are many ways you can actually display these, and I just added a whole bunch of these plots right there. Clustering analysis, again, clustering is I don't mean like doing k-means analysis or any of those clustering. Clustering in this case is very simple and straightforward. You have an alpha value, you have a correlation R value, right? Which means the higher the value, the more correlated these two parameters are. And we'll just look at distance in this case, which is 1 minus the correlation. And that distance tells us how close two different variables are, and then we'll plot those. Hopefully things make sense once we again get down to code and then start looking at the results. I think I put the notes down here. Convert the similarities to distances. So highly correlation variables are close. So we are converting that to distances. And Bootstrap is, again, we talked about the Bootstrap. So I think this is a good way of understanding what we achieve out of this Bootstrap, right? So again, earlier we can say we found R equals to 0.65, but is this reliable, right? So now we can say if we collected 1,000 different samples of penguins, 95% of the time we'd get correlations between what, I showed you the histogram plot of low up limit and then where the mean lies when it comes to the Bootstrap correlation. And that's basically in English right here. And hopefully you know how Bootstrap works. Randomly resample our data, how many ever times, and then get those correlation estimates. And we're just looking at the plot. And what else? Power analysis is straightforward. So I don't think we need to spend any more time looking at these. I'm just trying to see anything requiring a bit more explanation. So let's jump into the code actually. So step number 1, we calculate the confidence intervals to Pearson R. How do we add confidence intervals to our R value, whether it is Pearson's or Spearman, whatever? If the Pearson R is normally distributed, it's pretty straightforward. If it's normal distributed, you can get the critical values from the normal distribution, right? But oftentimes they're not normally distributed. And I talked about transformation. How do you transform your data in one of our earlier tutorials? We can use Fisher's Z space. We can convert our R to Fisher's Z space. And typically this conversion approximately converts or distributes our data into normal distribution. Once it's normally distributed, we can use standard techniques, which is the standard error in z-space using n number of samples, right? So then you can find out the standard error. You build your confidence intervals in z-space, meaning you know what the confidence intervals are in your z-space, but that doesn't mean anything. You need to convert them back into the original R space. So what do we need? We need Fisher's z transformation, which is, the equation is given down here, 0.5 log of 1 plus r over 1 minus r. Okay, so that converts our R values into some sort of a normally distributed space, z space. And we need to convert the z back to R, and that's what this function is, inverse of the Fisher right there. And once you have these Fisher z, we can actually plug those to get our correlation confidence intervals, which is you transform your R into z, and then you get your standard error, and you have your critical values, you have your lower and upper critical values, you're subtracting that critical from z and adding that to get the lower and upper critical values. And then you convert that lower and upper critical values back to the R space using our inverse Fisher z. That's pretty much it, okay? So that's the first part. The next thing we're gonna do here is correlation matrix. So we're going to calculate pairwise Pearson correlation, that's tough to say, pairwise Pearson correlation for each of these values. That's nothing new. We have done that previously in the last and the one also before that. So that's standard. Then we're going to build confidence intervals for each correlation using this above method. We get the confidence intervals, right? And we are going to get in a way, think of this as calculating three correlation matrices. One is with the regular way, the other one is using the low limit, and the other one is using the higher uncertainty limit for your R values, and then calculating those. Okay, and of course, storing and displaying and applying multiple comparison correction, basically Bonferroni or whatever. I think I described what these are at some point. I'm surprised. Did I not write it down here? Just a second, because it sounds fancy, but Bonferroni is nothing but instead of 0.05 or whatever the alpha value is, you're just dividing that with number of samples to get a different alpha value. So let's go, meaning a smaller alpha value. I apologize. I thought I added that notes. Oh, I did add that notes. Okay, so right here. So when we apply the corrections, it's very straightforward. When you apply the corrections, it's actually it's a standard library, like multiple tests is the library from did I put it here? Stats models.stats.multitest. And of course you supply the p-values right there, but the method is also the one that you supply. And here we are going to use either Bonferroni or Holm or FDR, two different types of FDR. Yeah. And Bonferroni is nothing but typically we use a p-value, for example, of 0.05. Well, let's make that condition a bit more strict. So in our case, we have 6 pairs. Excuse me. So our 0.05 becomes 0.05 divided by 6, which is basically 0.0083. If our p-value has always been 0.000 something, we don't have anything to worry about because it's statistically significant by applying a stricter alpha value right here. I hope that makes sense. So that's basically the key essence of this block of code. And the next block is basically correlation visualizations. Again, there are a couple of ways we are going to look at this correlation. We'll look at the results, and that makes sense. Hopefully, once we look at the results, and the next block should be the hierarchical clustering. And here, how are we going to do this clustering? Well, first of all, the way we cluster is by using a metric called distances. And the distance is basically 1 minus your absolute value of correlation. Yeah, if your R value is 0.5, for example, then distance is 0.5, right? 1 minus 0.5. So the closer the values, the closer they are highly correlated, like they're close. And We are going to perform hierarchical clustering, meaning apply these clustering, the Ward's method, to group of similar variables based on their pairwise distances. Yeah, so you'll again look at the dendrogram we already did look at it, so you know what to expect. And of course, we're going to visualize the results like by plotting this dendrogram showing the variables that cluster hierarchically. And of course, we're going to print out anything here. The code should be pretty straightforward, like distance is 1 minus absolute value of correlation. And the distance is basically, one thing, ensure the matrix is symmetric and has 0 diagonal. What does that mean? Of course, when you have the same variable, it's the distance to itself should be 0, right? So that's what we are trying to ensure right there, and convert to condensed from for SciPy, which is basically when you actually perform the linkage, which is the hierarchical clustering method. It expects a 1D value, not a 2D matrix. So we're going to take that 2D matrix, remove the diagonal and only the correlation part between variables, and then convert that into 1D. Yeah, that's what that function does up here, or that line of code up there. And then the rest of it is just plotting. Okay, we'll run all of this and look at the results and end this video. Now, Bootstrap confidence intervals for correlation. We talked about this a couple of times. Calculate the original correlation just like we normally do, and then generate a Bootstrap distribution, which is basically repeated resampling from the data to create like new data sets. And then we compute the correlation for each of those incarnations of our data. And then we get, for example, a whole bunch of R values, right? Then we actually compute the confidence intervals for those. Using, again, we say, hey, that's normally distributed. Go ahead and get your confidence intervals, and then show between 2.5 to 97.5th percentile of basically 95% confidence interval. That's the histogram plot we saw earlier in the PowerPoint, one of the PowerPoint slides. And of course, visualize and report key statistics. I kind of plot QQ plots usually along with anything that has to do with normal distribution being a requirement, just so we can see, visually tell if it's, you can perform Shapiro-Wilk test and then print those out, but plots is easier to see when you put them side by side. Okay, I think that's pretty much it. And finally, oh yeah, forgot about power analysis. This is again, I've done this a couple of times in the past. So it's basically what is the desired power, for a given target, or you can ask a question. If the power is 80%, calculate how many samples do we need. Again, we talked about this in the PowerPoint slide. And the code part I'm not explaining. Literally, you can actually take this, put it in ChatGPT, and ask it to explain line by line of the code. This is as long as you understand the high level, what exactly is going on from a statistics point of view. The code is, I hope you'll realize, is the easiest part, because I'm not doing any tricks. It's basically you get whatever the function is required right there from the scipy.stats or whatever your favorite library is, and then go ahead and calculate, in this example, the power. Okay. Also, although I did explain this in one of our earlier videos, that's why I'm kind of just browsing through the code at this point. The final section should be about how to report. Actually, after this reporting, I just added a bunch of text so we can actually see how to report based on some of the results we got. So I just ran all, so it should have completed. This should be pretty quick. At this point, all I'm doing is reading the Penguin data and actually calling each function that we just defined up there. Okay, let's start with, is this the top portion? Let's actually go all the way to the top of this section. Okay, here are the results. The first function, where we did comprehensive correlation matrix analyses. Previously, we had R equals to 0.653. Now we have plus or minus, because we performed these confidence intervals. We did the Z transformation, and then the reverse Z, where we got these values. The p-values are all much smaller than 0.00001. And the total number of data points we have are 333. And the correlation matrix, this is the normal correlation matrix. We have been plotting these in the last couple of videos anyway. So this is our normal correlation matrix. This bottom part should be up there, but obviously it moved it down here. And when you perform your multiple comparison correction, Bonferroni, Bonferroni, not Rini, Bonferroni, Holm, FDR tests, basically all 6 out of 6 came out to be statistically significant. So in our case, okay, the answer is we performed these tests, corrections, and still we find statistical correlation between which one did we test? Between these all 6 right there. Yeah, we did all 6 pairs. Okay. Now the visualization, you can actually see one way to show the visualization is adding the number of asterisks. So here you can see all of these are much smaller than 0.001. So this kind of tells you, okay, they are all statistically significant correlations right there. This is a couple of alternate views. For example, if you look at p-values, and this is where 0.05 is, and this is where all of our values are near 0 basically, yeah, which means very high statistical relevance, significance right there. There's not much, again, you can look at those plots. The next part here is hierarchical clustering. You can see how these two, the way to read this is these two are more correlated, and that combination, like these two, you see how this is going to the bill length. So flipper length and body mass are close in this distance, clustering wise. And then these two, flipper length and body mass, are closer to bill length. You can see where the bill length is right there in terms of distance. And then these 3, bill depth, but not really that close. I mean, bill depth is up here, 0.7 almost. Yeah. So when you look at this, and when you look at the plot down here, flipper length versus body mass is 0.873. So they both are kind of correlated, as you can tell. Yeah. So this is a nice visualization right here. So a bit more explanation in case you need that, but if you come down, you can see the Bootstrap confidence intervals, flipper length versus body mass. So this is the Bootstrap results, of course, and original sample size is 333, Bootstrap samples is 1000, so it's obviously going to duplicate some of the ones that we have. It would be nice if we have a larger data set, so you can this becomes even more strong. I should say. In fact, I should have changed Bootstrap samples to, I don't know, 100, for example. So it randomly subsamples within these 333. So I'll leave, I mean, code is right there, so go ahead and experiment with that. Either way, the correlation, original correlation was 0.873. Bootstrap is 0.873 almost, and not much Bootstrap bias. If there is Bootstrap bias, you would see bias right here. And here are the confidence intervals, and here are the Fisher's confidence intervals. They're practically identical. You may argue that, okay, you have a lot of, I have a lot of duplicates right here, but still usually this works very well. Again, I'll leave it to you to actually use 100 samples. It's just an input parameter in the function, so you can change that easily. And this is the plot we saw earlier, where I already explained it, and here is the QQ plot, so you can see almost aligned with the diagonal, so it's not bad. It's almost normally distributed. You can tell that visually also. And why is it important for it to be normally distributed? I mean, to get all these confidence intervals and etc. That's a prerequisite. The data must be normally distributed. If not, you need to convert that into another space that forces normal distribution, let's say, or at least assures normal distribution to some extent. Power analysis, we talked about this. Again, there's not much to show here. Again, this is the 80% line, And if you want to achieve 80% power, how much data, what's the sample size required for each R value? So if you look at R equals to 0.2, then you need to achieve 80%, that you need, where is R 0.2? Yeah, right here. You need about 200 data points, or one less than 200. And we have 300, so we are actually okay. Other ways of visualizing the power, so I'll leave it to you. And finally, practical guide for reporting correlations. How should you be reporting these? And the standard format, and I gave you the APA format. The standard format is, hey, there was a small negative correlation between build length and build depth in millimeters with a R equal to minus 0.229, and within the parentheses, you have the samples, number of samples, right? APA format is very similar, build length and build depth. I should have put lowercase m right there. Sorry about that. Build length and build depth were significantly correlated, and R value, P value, confidence interval, and the confidence range right here. There are a couple more examples down there. And here is the final summary of all correlations, as you can see. And of course, if you have done multiple comparison correction impact, then you can say all 6 out of 6 basically have passed. And I added some notes in terms of how to interpret the plots and everything, in case you don't want to have this video that you're watching next to you when you look at the results. All the results are down here in terms of how to interpret the plots and some of the results that we just reported. I hope you found this advanced analysis tutorial to be useful, and the next one would be the last tutorial in the mini series of correlation. The next one will be focused on correlation versus causation, very, very important. And I think I'll talk about ice cream and summers and stuff, probably. So please stay tuned and come back for the next tutorial. Until then, please do not forget to hit the subscribe button. Thank you.